Hello again. My name is Ed Blumdahl, and tonight I'm going to talk about a concept within astrophysics astronomy, and that is the title of my talk, The Expanding but Not Accelerating Universe. So it shouldn't take too long, but before I do that and get started on the expanding universe, I just wanted to bring to your attention that I did make a video not too long ago, and the title of it was Breaking the Light Barrier, Breaking the Light Barrier, Adding Velocities Beyond the Speed of Light. Forgot my own title. And I go through basically a conceptual talk, a model, much like what I'm going to do tonight. I went through a conceptual model, but I showed that the problem really with the special theory is the Lorentz factor. And most people who are familiar with physics and astrophysics know about the Lorentz factor. And I made the point that Maxwell, James Clerk Maxwell, never said that you can't add the speed of light to the motion of its source. And once you understand that, then you can see that the Lorentz factor has no bearing anymore, and you can add the velocities, to the speed of light with the motion of its source to have velocities greater than the speed of light. Of course, this contradicts what Mr. Einstein had said about that. But I did want to add this. There's a really nice book. I got this, I don't know, maybe 5-10 years ago. Einstein's 1912 manuscript on the special theory of relativity. And it goes through the 4 papers that make up the special theory, that now make up the special theory of relativity. And I just wanted to read something right out of this book. You can still get it. I think it's $25. I know Amazon has some. And it's a nice book. It's very historic, even if you don't agree with everything in it. And here's what Mr. Einstein himself said, page 84. He said, "This change of shape consists in a 1 to the Lorentz factor contraction of all lengths in the direction of the motion," right? So H.A. Lorentz, Henrik Lorentz, had already introduced such a contraction hypothetically. So Mr. Einstein is using the word hypothetically when referring to the Lorentz factor himself, right, in order to explain the negative result of the Michelson and Morley experiment from the standpoint of theory. So that's another important piece of the puzzle as to why the special theory of relativity isn't valid, right? Einstein himself is talking about the Lorentz factor as hypothetical. And once you understand that Maxwell never said that you can't add the speed of light with the motion of its source, you can see that the Lorentz factor falls. And since the whole theory, the special theory, is based on the Lorentz factor, then it's incorrect. So I just wanted to catch you up on that before I begin the topic here. And so the talk that I'm going to give tonight is the expanding but not accelerating universe. Because as of right now, the current thinking is there's a couple of papers that came out in 2012 that the universe is expanding, is accelerating. And I basically disagree with that. And so I do this, same as what I did my other video, is a very conceptual thinking. In other words, oh, by the way, this is the Lorentz factor right here, which I'm going to erase in a second if you might not see it. So the current thinking is that the universe is accelerating. And I disagree with that. And to me, I mean, you can add all the math you want to the models, whatever they are, whatever people have. But if you're doing the basic conception, how it works, how it's put together, right, the math will follow. If your concept is right, the math will follow. If you do the math, it doesn't necessarily mean your concept is going to be correct. That's why I start with the concept, right? If it makes sense, it holds together, then that's a good concept. So I've covered that. It's going to be a little bumpy. I kind of have my notes here, so bear with me. Hopefully, you'll at least get the major idea out of this. Obviously, it's standing as the universe is expanding, not accelerating. So the papers that came out, forgive me, I forgot the year, but on an accelerating universe, right, they used type 1a supernovae, right, in nebula, right? And they looked at these and they looked dimmer, and so therefore they thought, well, they're dimmer than what they should be, and so therefore they must be farther away. The luminosity is not as much. So that's how they got the accelerating universe. But what they're basically, so they use type 1a supernovae, and then within this, to explain the accelerating universe, they use dark energy, lambda. Lambda is greater than 0, dark energy. But the dark energy that they're using is really resurrecting Einstein's cosmological constant, which even he threw out. And so I really question that. They can't define dark energy, right? They just said it's out there, and the reason why it's accelerating is because of dark energy, but they have no definition for what it is. So, the question again is, so if you're starting with the Big Bang, wherever it might, from a singularity or greater, inflation theory, right? They use inflation theory, dark matter. I think dark matter is probably there. It makes sense. Some of this other stuff doesn't. But let's say, the Big Bang might be a singularity. It might not. I don't necessarily agree with it. It's just extrapolating back on Mr. Einstein's field equations. I don't necessarily agree with that. But the whole idea with the accelerating universe is, let's say, the Big Bang, and these are maybe galaxies or whatever moving away, is that it's the same galaxy. So you start here with, the acceleration, from the first galaxy, which leads to another spot farther along, right, with the second acceleration, and then it leads to another spot, the same galaxy, to yet another acceleration, through another acceleration. So it's the same exact galaxy, just, is at one velocity here, acceleration, to another velocity here, to another velocity. The velocities keep increasing, right, because it's constantly accelerating. But it's the one, right, it's the same galaxy that's going through all these changes. And talking to some of these people, I mean, they sort of got the idea of Hubble's law, that the farther that these nebulae or these galaxies that we now understand them, the farther away the faster they're receding, right? So they get the right idea, but I think the application is wrong. Here's Hubble's law: velocity equals h, which is just simply Hubble's constant, and d is the distance. Again, you can have parsecs, you can add math to this, whatever it is. It's not going to change the underlying concept. So you can have a constant acceleration, you can have an increasing acceleration, and you can do all kinds of things with it. But the idea, which I said out of this is important. One, dark energy. There is no definition for dark energy, just like there is no definition for space-time in the general theory sense, right? If you're going to have space-time and space-time bends, then you have to you have to define the material reality of the composition of space-time, right? You can't say it bends. What's bending? You have to define that. It has to be substance. It has to be something. You can't bend empty space or a void. Has the same kind of problem. So it's just that this one galaxy is just accelerating and moving on. You know, I suppose you could put other galaxies doing the same thing and moving on, but it's that one galaxy. Now, this is how we changed screens in the old days. Now, this goes back to really an explosion. If you look at some basic explosions, you know, that we've seen, like fireworks, or it could be basically to a pipe bomb, you have anything where there's sort of layers of material that blow out, and you look at how they act, that's sort of the way nature acts as well. So like here you have a fireworks, right? And I put it down here. There's the bursting charge, you know, within it. There's 3 layers of what they call stars that come out. You know, you've all seen those big orange fireworks that, you know, start and come out into this big ball, right? So this one would have just orange if that were the case. Here I just put 3 colors to make things obvious. So you have red stars on the outer layer, green stars on the next layer in, and blue stars on the next layer into that, right? So you have bursting charge within this. You have a black powder lift charge up in the air. But what do you get? What's going to happen is it goes up into the air for a certain height, and then the fuse hits the charge and it explodes. And what are you going to get out of it? You're going to get that the outer layer, the red are going to go faster and the furthest, right? I mean, what you see as it explodes out, the outer layer, whatever it is, will go farther and faster. The green, the inner layer to that will go out fast, but not as fast, and it won't go as far. And then the blue stars, what's going to happen with those is they go less fast and they go less far, right? So you have the layers going out like that. Now, yeah, blue follows, green, fast but not far. Okay. So there you have, you know, like an explosion. Even a type 1 supernovae or supernova, right? It basically acts under the same kind of process, right? That it's going to collapse, it can expand and blow out, but it's going to basically follow this pattern. The outer layer is going to go out faster. The inner, you know, the next layer is going to go out fast, but not as far, and the inner layer to that. I mean, it's going to follow that process as it kicks out matter into the universe. So what I'm saying here is, I'm just showing. So that's sort of the general, you know, a firework and the general framework of how the physics of an explosion or a bomb, right? It just has the bursting charge, and then it has the material. It could be a gravity bomb like they had in World War II and going off and whatever. If you look at it, so it doesn't, in other words, when you're looking at these, they'll go out to a certain velocity, but they're not accelerating per se, right? The bursting charge, they go out to a point and they stay at a certain velocity. What happens if you go into space and you have a cartridge, a bullet, and you put it into a firearm and you shoot it? Well, you can actually shoot a bullet in space because the primer sets off oxygen, has its own oxygen, goes into the powder, it burns because of the powder actually burns. It doesn't explode, but it's so quick it sounds like a bang, but it actually burns, forces the bullet out of the barrel to the muzzle, right? And once it hits that muzzle, that's the velocity. It will accelerate up to a point. Once it's out of the barrel, it's going to travel at whatever the muzzle velocity is, right? At least on Earth, right? But in space too. So I just drew this up really quickly. It's more qualitative than it is quantitative, but it sort of gives you the idea what's going on. You know, you start off 0, 0. You're firing, let's say you're firing a bullet. It'll begin to accelerate. The velocity will start to increase. It will sort of hit a high, or the maximum acceleration. It'll start to low. It'll start to break off. Here it's still increasing, but it's increasing, starts to increase at a decreasing rate. And then at some point, when the acceleration is no longer pushing it, it'll go off into a straight line, following Newton's first law of motion, right? So, I mean, that's just a basic concept of how it works. Everybody's familiar with it. But it has an important bearing on understanding of how the universe is expanding, right? How it's expanding out. So you have an expanding universe. And the difference between an accelerating universe and an expanding universe is in the interpretation of Hubble's discovery, which was in the late 1930s somewhere, right? Those galaxies that are farthest away travel the fastest, right? And then as they move in, they're traveling less so. But like here, there's just one galaxy accelerating. Here you have four different galaxies accelerating. In other words, just like we had for the pipe bomb or the firework, right? The Big Bang, an explosion, throws matter into the universe, right? And what you could call the surface material or surface mass would be blown out, what? The fastest and the farthest. What happens next? Well, the underlying layer to that would be going out not as fast, not as far. It'll still be moving. The same thing with the one even inside that and the one inside that. So these are four different galaxies or masses that are being blown out, but they're all different, right? So Hubble's interpretation in this case is the velocity of this galaxy is the highest, right? And it's moving away from us the farthest. It's farther out. And this one, they just follow in a line, just like we had with the fireworks. So here, here it makes it makes sense. I don't need to explain the expanding universe. I don't need dark energy. Can't be defined anyway. I've never heard a good definition of it. And you have the Einstein's cosmological constant, right, is 0. It's unnecessary. Inflation theory, you don't really need it, because if the Big Bang, what started from, isn't a singularity, then you can adjust the size of the original mass, to fit what's going on in the universe based on this. So the velocity, the first velocity is the highest, the second highest, third highest, fourth highest, right? Dark matter, I think it's logical that dark matter probably exists. I can see that. Dark energy, I don't see. I don't need inflation theory. I don't need a singularity to start off with, and I don't need the cosmological constant to be in there. Now, the papers, if you go to read the papers, I'm not going to cite them here, but you can go look them up. They do a lot of statistical analysis of trying to determine, certain aspects of their model for the accelerating universe. But I'm pretty well versed in statistics, statistical modeling, and so forth, and I don't really think much of it. So I don't really agree with a lot of it. And that's why that's why I'm bringing this to people's attention, that I don't think it is accelerating. It's just expanding, just like Hubble said it would. I mean, the interesting part is if you start to go back and you look at different gravitational models that people are building, they look a lot at, if the universe is accelerating or not, right? I mean, that depends, and I'm looking at papers and you're saying now, well, they thought they had it, except that, it came out that the universe is actually, or the matter's accelerating, right? And then they have to get rid of that because if they have an accelerating universe, something else doesn't work in the model and whatnot. Here you can start over with what? A basic expanding universe, right? So you don't need a lot of that other stuff. Yeah, so I mean that's, and like I said, one of the other reasons I like I do this all the time. I mean, even if you look at my other video about breaking the light barrier, it's very conceptual. I use the Lorentz factor. That's the only math I think I use in the whole video. Same thing with this. I mean, the concept fits. The concept works, and when you look at like what Hubble actually said, this fits right in exactly with what he said. We don't need an accelerating universe, and I don't think it really works. So that sort of brings, actually that's sort of a quickie. Let me see what I'm doing here. Yeah, I pretty much got all that stuff. By the way, just so you know, my name is Edward A. Blumdahl, and this is blumdahl300@gmail.com. If you have any comments, I mean, I'll be glad to listen to any comments within reason, I guess, as we all get kind of excited about what our own pet theories are. Yeah, and then, so like I said, there's certain ways, I mean, if this is correct, if it's only an expanding universe, then that's going to change sort of the shape of perhaps the universe, but it's certainly going to look at a way it might change our understanding of gravitation within the universe, right? I'm not sure that, like I said, I mean, I've gone through the general theory, and I think there's major problems with the general theory. Certainly, I don't think the gravitational view, I mean, his view of bending space-time, I don't think it's really there for the same fact that you can't define it. I mean, there's nothing to define it there, so I think that's a regular problem. So, if you have any questions on this, I sort of ran through this relatively quick, but there's not a lot of math here. It's basically just a conceptual model. Like I said, what's key is the two aspects: how an accelerating universe works versus how an expanding universe works, right? And if you understand the difference between these two, then you basically got the idea. So I think that if you have any questions or anything, like I said, you can contact me at blumdahl300@gmail.com, and I'll be glad to furnish any questions or answer any questions that you have. Let me say one other thing about the universe and the expansion, is that I don't agree with the fact of what has been, I guess, maybe accepted theory at this point, that the universe has space-time like a fabric, and within that space-time, all the objects are kind of embedded within the space-time, so it's actually space-time that's moving, and the objects are caught in the space-time like a spider's web and kind of move with it. I absolutely 100% disagree with that. I mean, space to me is space. It's empty, it's void. Objects are freely to move back and forth or wherever they want to go, depending on the forces, that are acting upon them. Or the gravitation, I mean, even like Newton's gravitation, right? As to the path that they would take. So I don't really think that space-time and this idea of a sort of like a net with the object embedded in it works. Space is empty, objects are free to move based on the forces acting upon them at any time. So I think that's it. I hope you got most of it. And like I said, if you have any questions, you can give me an email, and I'll be glad to answer them for you. So that's it. Good night. Thank you.